A simple model here, and forget about the logarithm, that's what you need to do for the Poisson. Basically, the frequency with which they have pretend play is an intercept plus, I'll put the word slopes in quotes, times phase. It's just a phase difference. It's saying they're flat during the baseline phase, and they jump during the treatment phase, and they're flat during the treatment phase. There's just a dummy, this is called a dummy variable. Phase is either 0 for baseline or 1 for treatment. So it's saying that behavior is at one level during baseline, jumps up, and is at the other level during treatment. That's something that almost never happens, but it's what we always hope is going to happen. So here's what happens. How does the average child behave? Now this is where we run into trouble. We get something that isn't very interpretable. Even for people who are statisticians, they have to stop and think about this. What is negative behavior? Well, this isn't negative behavior, it's the log. The log of the amount of behavior is negative. If you exponentiate it, it'll be positive, but very small. It'll be less than 1. Remember those phases were pretty flat around 0, so it means the average amount of pretend play was essentially less than 1 for the kids, for the average kid. And this shows a big change in average play going from the baseline to the treatment phase, and it's significant. And the amount of change, we can not only estimate it at 2.55, and that probably doesn't mean much to you, but I'll show you in a minute how to translate that to something more meaningful. We can also get a confidence interval by going up and down a couple of standard errors. We get a confidence interval on that amount of change. So we not only know what the estimate is, we know how well we've estimated it. So unfortunately, doing this is not straightforward. And it means that a lot of people doing single case research, if they want to get into the analysis of things like this, have to do it as a team. In medical research, that's done all the time. There are no medical researchers who do their own statistics. They have biostatisticians. And I think in psychology, not just single case research, but in most of psychology, the time is coming where most research will be done as a team. And there'll be a statistician on every team who can do these kinds of things. So I don't think it's worthwhile for every single case design researcher to learn how to do this kind of thing. It's beyond what you want to do. I mean, you'd be putting in too much time. You could take one statistics course, fine, 2, fine. But if you start piling on lots of statistics courses, it's like I didn't join this to be a statistician, I did this to change behavior. Right? So I don't think people should do that. I think we should have teams of researchers doing things. And that dependent variable is hard to interpret because it's the logarithm of a count. Right? But you can change those back by exponentiating. It's just reversing, taking the logarithm. And that's a number, the exponential of minus 0.8 is 0.45. That means about a half of one of those pretend, fantasy or whatever, pretend play per 10-minute period or whatever, however they were measuring it. So it's about half was the average. So it's almost none of the behavior occurred on average. The change from baseline to treatment phase is 2.56 was the number I estimated. So you have to exponentiate that to reverse it. So that is about 13, right? 12.94 is round off to 13. So what that's saying is there's a 13-fold increase in the amount of that kind of behavior due to treatment. So that, the hidden, we could hide all this logarithm stuff and Poisson, we could hide that behind the scenes and just tell researchers it increased it. This is what the rate was before, it was about a half, and we increased it 13-fold. That's a lot more palatable than saying the logarithm of the number of events was, minus 0.8, which doesn't go over very well when I've tried that. Okay. So this is a lot better. You can translate a lot of these things back into things that make sense to people, I hope. Then one thing we didn't look at in the previous study was variation across people. So is there much variation across people? We can express that in terms of a standard deviation. So this says, well, the first one says there's a lot of variation across the kids in the intercept. We don't care so much about that. What we care about is the treatment effect. Was there much variation? And it doesn't, it's non-significant, it turns out. But it's enough maybe, you might want to look at it in the future. The reason it's one reason it can be non-significant is lack of power. We only got 5 kids, and you're almost never going to have enough power in single case design, but you test for it anyway. This is another thing Rob pointed out. Statistical significance down at the bottom is not the same as practical importance. You've got to look for both of these things. And what I did here was I added cognitive age as a predictor of variation in where they started, the intercept of the previous equation, which was their baseline behavior. Not that that's of any interest in terms of the effect, but just to demonstrate how this works. And you can see that cognitive age that was measured as anywhere between 14, I think, and 22, that had a significant effect on where they started. So the higher their cognitive age, it turns out, the less of this kind of play they had before the treatment, which I have no idea of why that is or what it means, but I can just point it out to the people who did the study and say, hey, look at this, it's something that might be of interest. So I don't know anything about pretend play, but so I don't know why it might occur, but there it is. Let's see, is this any? That's, okay. And at that point, you can test for remaining variation among the kids, and finding none and the effects being small, I stopped at that point. And I think, oh yeah, remember that one kid who didn't seem to respond at all? He also happened to have the highest measured cognitive function, which we just found to predict baseline rates. So I decided to do an analysis of Kirk as an outlier. Is it just Kirk's very different than everybody else and everybody else is the same? So it turns out that if you compare the two models, cognitive functioning does a better job of explaining a variation in baseline counts than does knowing whether or not the subject was Kirk. But I prefer the model with Kirk as an outlier because the predictions for the model with age, cognitive age, are really odd. And the effect of each year of cognitive age is too large to believe, and therefore it's being distorted to fit Kirk's behavior. So the bottom line is down at the bottom, where Rob said, you should look at your model for what's going on. And sometimes substantive information trumps a statistical fit. Even though something might statistically fit a little better than something else, doesn't mean that's the right thing, and you have to look at the reason behind things. And if you have good reason for believing that you've got an outlying person rather than that variable being a good predictor, then you go with that reason. Let me see. This one I'm going to wait for till this afternoon. So is this a good time to break? All right. Are there any questions?